And since our system only has that structure, so the superconductivity has to come up from here. Right. So there's a common feature in all systems. And with it, you can see this should be the ideal system to study. Right? You can see a lot by simply looking at this particular system. And that's what I'm going to tell you about it. For example, if we look at the resistance curve, this is the iron selenide. This is coming from the crystal, but actually the polycrystal similar, because all the structures, because the basic structure is so simple, so even polycrystal you will see the same characteristic. Immediately you can see that this is represent a one layer or even multi-layer, And the resistance curve, you can tell there's a feature here. Right? For metal, usually you see a linear curve, but while here it's going to saturate at much higher temperature. What's going on here? So there's some feature simply from this curve. And there's a dip, although small, but obviously there's something going on. Of course, superconductivity at lower temperature. And we, at the beginning, we already asked ourselves, are this common? Or just specific in this particular selenium system? And in fact, you examine all the good data or good sample, they are similar. So this is the so-called 1-2-2 compound. Actually, I got this from Chu. They were working on that later, and a little bit different in composition. But you just look at it, the temperature dependent, almost the same, except that the TC is much higher. But there is also some feature at much higher temperature. So immediately you can tell there are some interesting feature here. And furthermore, if we look at the transport again, okay, for iron selenide, we measure the so-called thermal power. Okay. And you can see that without going into detail at the higher temperature, of course here, we're probably somewhat related to the higher temperature anomaly in the resistance curve. Most pronounced is this one, at around 100 Kelvin, where the resistance shows a small dip. In fact, here it shows there's a local maximum in thermal power. Okay. And what is this in fact a general too? In fact, yes. We compare the other system. This is so-called 1111. This is 122. When they are superconducting, you always see the kind of local maximum in thermal power. For a non-superconducting sample, then you don't see it. Okay, so that, from the property, will tell you this interesting thing. And that is another system. This was a much later discovery in China. Basically, it's a follow-up of our work, iron selenium, they put in some potassium in between the layer and stabilize the phase and get superconducting. And for the superconducting region, that the composition that becomes superconducting, you see those maxima here. For non-superconducting, then you don't see it. Okay, so that tell you this is something really important. So experimentally, we have to identify what that is. And theoretically, we also need to learn more about what is going on here. Okay. So, what in fact, right after our discovery, we already did some more detailed analysis, as we see here at this temperature, and we knew right from day one. Okay, that is associated with a very interesting result of the structure, from the structure point of view. This is the plotting of this tetragonal crystal with three angles, alpha, beta, gamma. Right? Usually they are all 90 degrees at high temperature. But around that temperature, you can see that the gamma angle, okay, start to grow. Okay, it starts to grow. And then saturate at a certain value at a lower temperature. And that indication this structure distortion coming. Okay, from a tetragonal become a slightly distorted to ortholombic. And that is where the thermal power maximum and the resistance curve happen. Okay, so we knew this is the structural distortion, and schematically it will tell you that this gamma angle is changing, although very small. But I think it's just critical to changing the property of it, which means that along the axis you have one, stretch it that way and then extend it that way, and then put in this is gamma angle to increase. And more importantly, we were able to identify. There are two work. One is from a group in Princeton, Bob Carver in Princeton, and they follow our work, and then they make the very important or beautiful demonstration that by changing this stoichiometry, slightly only from 1.01 to 1.03, this change is very small, but at 1.01, which is superconducting, then you see this. This is plotting the lattice parameter. Okay, there is a distortion at low temperature after lower than 100 Kelvin. But for the 1.03 sample, which is non-superconducting, then you don't see that kind of distortion. Okay. So that gives you a very important conclusion that distortion is essential, critical to the superconductivity. And I collaborated with Minjie here, and we did some thin film work, okay, using the iron selenide. This is a little complicated graph, okay. We're making the nice epitaxial film, and while we demonstrate that, because the pinning with the substrate somewhat, you can make it superconducting, like this blue curve show, or non-superconducting, okay, depending on the process and the material. And for the non-superconducting, and we did the very careful low temperature structure X-ray determine what the structure is. And we show that for the non-superconducting one, then the low temperature phase, there's no distortion. But for the superconducting one, and you can see this the peak, a single peak, split into two, indicating this distortion comes up. Okay, so that also further proof that no distortion at low temperature, no superconductivity. Okay? So immediately, this is one consequence or a correlation we can conclude in this particular system using iron selenide. And I believe the same thing for the other so-called 1111 or 1111. And up to that, actually, because the theory, there's no such a clear theory about what's going on. Okay? So this is something I think I've been talking to TK to look into what's going on. But furthermore, we're using some optical probes. Using a femtosecond optical palm probe technique to look at the material, either thin film or single crystal. Okay, and this is the typical setup we have. What we are looking at is what based on the interband transition to see how this excitation related to what we have observed. But to make the story short, without going into the detail, okay, here's the summary. When we cool down the sample, okay, we show that around 40 degree Kelvin, indicating some kind of optical absorption. Okay, and there is some kind of spin fluctuation associated with that to show up from this the amplitude and the frequency change, and some more detailed feature indicating there's a gap open. And all at this temperature or a little above. Okay? And also we can, by looking at this phonon, acoustic phonon, show that the stone dynamic has a anomaly associated with it. So the conclusion of the whole observation is this: we understand, from experimental point of view, that at a higher temperature there's some starting at maybe around 200 Kelvin. This optical magnification started going on. And then at around 130 Kelvin, it showed that the changing of the shear stiffness and some optical absorption, they all happen about the same temperature, indicating the reduction of denser state around the Fermi level. And that also implies some spin fluctuation may be associated with it. And that induces a kind of gap opening, and essentially the distortion to be associated with it. And this whole characteristic and come to this superconductivity at lower temperature. Okay. Now how this story can be told in terms of a more complete theory. I'm just experimentalist, so it's really not my work. Okay. So this is the observation we have. Though it's not complete, there are more work need to be done in order to much better or well calculate. And the thing is that because up to now, we have only one single system, which is superconductor. So we don't have something like the earlier has a complete phase diagram, a whole series of compounds that we can examine by looking at how it comes from the non-superconducting to superconducting and how it evolved. If we had that, then the story will be more complete. Okay? Then we can tell more in terms of understand the whole situation. And what I'm going to tell you, the real excitement is the next, what I'm going to tell you here. Okay? Because in this uncertain, interesting, actually in 2008, okay, already people observed that it has an extremely large pressure effect. By applying external pressure, you can increase the superconducting transition temperature from 10 K almost to 40 Kelvin, a 4-time enhancement. Okay. And why? Okay, this is just really interesting question. And in our case, okay, let me go back to this curve. We also observe some interesting thing here. By, instead of just looking at simple resistance curve, let me just take the derivative of this curve, which can give you more detail what's going on. And this is, I think the student probably should learn that. You don't want to go into very complicated data. Sometimes the simple data, if you know how to analyze, it gives you some interesting feature. Here, I can show you that with the simple, just take the temperature derivative of this curve. Of course, you would expect an anomaly, maybe some above, okay, but here immediately you can see this is transition temperature because of the dip, so there's a peak. Okay, we can associate with that clearly. The superconducting transition, of course, big. What is here? So we see, every time we see this, around 40 Kelvin. And immediately give us to associate with that pressure effect, right, which is 40 K. Which means that, well, maybe already in this system already has this 40 Kelvin phase, right? Although it's small, only very small amount. Okay? So we'll be asking whether there is such a high TC phase exists. This is one question. And the second question, we have to answer from more material point of view. Why 1.01 and 1.03 make so much difference? One is superconducting, one is not. Only 0.02 in terms of chemical composition. Why is it so sensitive? What kind of phase we have, okay, in terms of material phase? And in fact, up to date, this issue is still not settled. Okay? Not really settled. And as I mentioned, okay, what is the exact stoichiometry? Okay, and people always, because of high TC, people always like to have the phase diagram like this to describe the system, right, in order to really get a full picture. And as I mentioned, of course, one single line, the TC here is not sufficient to understand, based on our high TC, high temperature superconductor experience. And so people have come up with all kind of models, and most people accept what I don't accept myself, but a lot of people think this is the phase diagram, okay? Because we did the work right after the discovery. We replaced the tellurium, we already know that is not superconducting, okay? Simply by changing this chemistry from selenium to a much heavier atom, and it becomes non-superconducting. And so people say, well, this must be the carbon, because they dope a substitute partially the tellurium by selenium gradually becomes superconducting eventually to 10K. Okay. So there's a range of superconducting transition, and there's some temperature. Okay, right here, this is the P, and here the high is the TC. Okay, here are some structures. So people have been using this as the phase diagram for the iron selenide. However, this is very different chemistry. And not only that, then you look at the structure, very, very different, okay, crystal structure. So at the beginning, I don't believe this. Okay, but what is the real phase diagram for the system? Okay, so that's our question, number 2. Okay, what the phase diagram of iron 1+ or 1- selenium. And in addition, this is more recent work. You know, this was done in 2008, about 2010, 11, and China group found that you can insert potassium to make it superconducting, and TC can be as high as 48K under pressure, and normally about 33 Kelvin. Okay, so you have a full series of a new phase comes out. And more exciting or surprising, or actually the puzzle, is that a Tsinghua group in Beijing, and they are using the MBE to grow a single layer iron selenide, okay, a 1 unit cell. And they said that this can have TC about 30 Kelvin. In fact, by using scanning tunneling microscope to look at the spectrum, and they declare there is a superconducting energy gap, which is as high as 65 Kelvin. Okay, and that was really a lot of excitement about more than a year ago, and a lot of work coming up. And I think there's a second group report also from Beijing, the Institute of Physics, and they're using different technique to probe the system, and the photo emission they also seem to give the similar result. So do we really have the TC about 65K with a single layer, and what all this all about? Okay, so that's the question. Another question we really need to understand. And another interesting subject is that for this particular system, up to date, no one can make it a single phase. No matter how good your preparation process, and it's always, for superconductor one, is always a mixed phase, which means the X-ray showed there's 2 different kinds of compounds. And one of it is this. It has a very interesting composition with a potassium of 0.8, iron 1.6, or selenium 2. Essentially, we write it as a 2, 4, 5. Okay, 2, 4, and 5. And which means that if you look at the layer, the iron, this is the iron selenium plan. You look at that layer, there are some iron atoms are missing. Okay, so you have an iron vacancy in order to be chemically, equivalent, right? So there must be some kind of iron vacancy in this system. And they found that this system, when you cool down to lower temperature, at room temperature, actually it's already stabilized as an older iron vacancy phase. And the iron vacancy will form into this kind of square root 5 by square root 5 order. And that becomes a non-superconducting insulator with kind of a magnetic order at very high temperature. Okay. So this is the mixed phase. It always is such a mixed, interesting phase. And so that's the question is, what is this phase is all about? Why? I mean, just from chemistry or material point of view, maybe this is just a stable. They cannot make a really good one single stable phase. But in terms of making superconductor, why it's always mixed. Okay, this is really puzzle, and it's really many people are trying to find the answer for this. So with all this, make you wonder, okay, some kind of interface or some kind of a fine structure are really critical. Okay? So that's make us to think, maybe we should think of a new way of study this system. Okay? So that's why we came up with the idea to start to think to study material in nano dimension. All right? And because our rationale is that to answer those questions, we speculate that the presence of defect is critical. Okay. As I mentioned, that kind of a deficiency, because the iron selenium never being one to one, the stoichiometry 1 to 1. We could never get that kind of stoichiometry. So it must be some kind of defect, whether it's an iron defect or selenium defect. We know that nanostructure provides important insight into the better understanding of defect. Okay, we have interest. This is based on the nanoscience study. We know this is one way to looking at it. The technique to fabricate this nanostructure are very well established after the past 10 years. We learn a lot from chemists in different groups. We know how to do that. Unfortunately, my group member very good. We have very good material scientists and chemists, and they were able to use a very simple process, okay, to prepare interesting particle oil structure. And this is one of the early work we had. And indeed, by using a simple process, okay, low temperature, relatively low temperature, you see that but this is the magnetic susceptibility measurement. Usually you see this kind of big signal indicating a superconducting transition. Okay? And we are able to see that properly make with the time and the stoichiometry, then you get some fade, which is the temperature is almost the same as the resistant anomaly I showed you earlier when we look at the derivative. Right? So this temperature drop, but this is a bulk sample, okay, without pressure, and directly by measure the magnetic susceptibility. So that's one proof. There's a small percentage of a superconducting phase around the temperature with this particular sample. Okay? And we were able to see much better signal, but a little slightly different chemistry composition. This is the ions of sulfur, selenium, and we did see much larger drop with the superconducting transition around that temperature. Okay, so that's a good proof or good indication by using nanoparticle, then we can stabilize some superconducting phase, which has a higher temperature without any external pressure. Okay. And of course, you can see this way with the nanostructure of the surface or interface already has an existing stress, so that gives you this feature. More interestingly, that my group members are very good. Okay? They know how to play the trick, so they were able to grow those kind of beautiful thin nanowire. And the process is simple. You just make a thin film or a little bit thicker film, and then put it into oven and near at a higher temperature. And because the substrate, the mismatch of the material, the film and the substrate, and push it out, and they eventually grow a lot of nanowire, okay, with a beautiful single crystal-like nanowire. Okay. So those are the wire, and we, India, and they are very good to put the wire into this kind of with the contact to measure the transport property. Okay. And the result actually was very surprising. We did see, superconducting transition, but only see it in iron, tellurium, sulfur, nanowire, or the iron, selenium, tellurium, nanowire. But we never saw it in this uncertain. Okay, up to date, we're still not yet complete, we're able to see a nanowire superconducting. Well, maybe we didn't try hard enough. We have so many wires, maybe certain composition we should try. But anyway, we were able to see but different characteristics, some metallic, some semiconductor. The transition actually of those that were very beautiful. It was TC, very sharp. So I mentioned it as a paper. So we have to look at what we have. So from the structure, the TEM, you can see that very nicely. And the diffraction show that we all have the perfect tetragonal symmetry, but one is not supersymmetric. Okay. So more detail, and then you analyze it. I'm sorry, this should be checked. This is 5 to 4, not 4 to 5. Okay, because the selenium to iron ratio we found it all close to 1.26 or 1.25, which is 5:4. Okay, if you remember previously, I showed you this potassium though you have a 2, 4, 5, and now we have a 4, 5 without potassium. Okay, that's just iron 4, selenium 5. Okay, it should be 5 divided by 4. So we have a 4 iron, selenium 5 in this nano one instead of 1 to 1. And as I mentioned, the 2, 4, 5 has the defect, which older becomes insulated. Okay. So this seems to match very well. Okay. So we're asking immediately to see whether we missed that. We didn't see clearly now there's some kind of defect or this kind of odor. And Maw-Kuen, I think, is in the audience, who was good enough. So immediately look at the TEM, and this is diffraction. So beautifully, in addition to those tetragonal spots, you see those beautiful rings. Okay? And by simple analyze, this is the superstructure with the square root 5 by square root 5 order. Exactly the same as the 2.5 I just made. So we don't need a potassium here. On the other hand, for those superconducting ones, and tellurium, selenium, or the tellurium sulfur, which are superconducting, you don't see that kind of a superstructure, no superlattice. Okay, those are the details. So that tells you, okay, you need to get rid of those in order to become superconducting. Okay, you do have a superstructure, which is the older defect. And that seems to be very critical for this system. You always have this kind of defect. And when this gone, then it becomes superconducting. So can we do something like this? Okay? Well, this is to give you more look at it and more detail about this structure. Okay, so this is the compare with the 245. This is the uncertain iron. We have looked at it, and this is the conventional, the paper. So they are identical. Right? But here we don't need any. Okay, this is repeat again. Okay, this is the 245 system. So we don't need a potassium to stabilize the phase. But interesting, you only see that in this banana structure for the bulk sample of the single crystal we grow. It's always go to 1 to 1. It's much easier to get into that fully. The stoichiometry become more close to 1 to 1. So we were able to also further look at that different Y, and this is a different dimension. And as I mentioned, we have this insulating or non-metallic one, and that always give you this kind of profile with the superstructure. But we also see, as I mentioned, we also see kind of a metallic behavior wire. And this is another wire which is measured by Nugent associate, and with different dimensions. And this kind of a wire, when we examine more carefully, okay, you probably don't see very clearly here when we have a mesh curve. But the chemical